Hey there, everyone. Ryan Schewel here. Welcome to my analytics channel. So, in the project today, I want to take a look at optimizing schedules for airline pilots and flight attendants. So, the motivation for this was basically um, inspired by myself being on a plane flying from St. Louis, Missouri to New York. Now, my wife and son and I were coming back from a short vacation in St. Louis, heading back to New York. I was talking to the flight attendant that was sitting at the back of the plane, just haphazardly, randomly saying, "Hey, how's your day going? And what's going on with you?" Stuff like that. He said this was his fourth flight of the day. It was about 2 o'clock, maybe 2:15 in the afternoon that we were taking off. And I thought, wow, you've already flown three times. This is your fourth flight. And he's going from St. Louis to New York. Now, I don't know if the guy came from New York to St. Louis on his first flight, St. Louis to New York second, New York back to St. Louis third, and then St. Louis back to New York fourth, or if he went to Louisville, Kentucky, or who knows, Charlotte, North Carolina, or something. He went different places. That was his fourth flight for the day. I thought, well, that must be very interesting how all these flight schedules are organized and hopefully optimized for the benefit of the business. And I started to wonder, how do you do this, right? So that was the inspiration for the project today. Now we can easily optimize flight schedules and multiple pilots or multiple flight attendants that work for any one given airline. So we can assume that we're working for Frontier Air or Alaska Air, JetBlue, Spirit, Southwest, American Airlines, whatever, it doesn't matter, right? We're just going to assume that we work for one airline and we're going to optimize the way that the business operates, okay? So we have a team of 20 people, and again, it can be anything. I'm just going to use 20 to keep it somewhat streamlined and simplified here. In a real airline, you're talking about probably hundreds of pilots and probably several hundred, maybe thousands of flight attendants. I don't know. We're just going to keep it with 20. I think that will illustrate the point. And if you have 1,000 people working for your airline, just scale up to 1,000 people, right? You can adjust the code very simply, very simple to go ahead and accommodate your needs. So we need to define the flight, define the problems, right? This is airline pilots and airline flight attendants flying between multiple airports each day, right? And given they'll probably have a day off, 2 days off, whatever, for their weekend. It could be Saturday and Sunday. It could be any random day of the week. But we're going to have them flying either 3 or 4 flights per day. That's the assumption here, based on my friend that I talked to on the airline. That was his sort of feedback to me, that they tend to fly about 3 or 4 times a day. So we have the required crew size, the turnaround buffer time. We'll need to construct a feasibility matrix. So I'll show you how to do that. We need a set of decision variables. Okay, so each variable represents a person or a flight. We need to define constraints. Okay, how many times can a person fly? What's the maximum? What's the minimum? Things like how much time is between flights, right? If your flight arrives in an airport and you have to go across the airport or tarmac or terminal or whatever the thing is called, you're going to need a certain amount of time to get from point A to point B. We'll say 60 minutes to get around, right? Between the time the plane lands and then the time the next plane takes off. You need 60 minutes to get your luggage and to run to the next one, right? So that's another constraint we have to add. I'll show you how to handle that. We're going to maximize coverage of flights, minimize crew idle time, and maximize the fairness. So even distribution for work. We don't want all the work to be piled up with a couple of people, and we don't want people sitting idle too, okay? So there's another constraint that we have to handle. We're going to minimize total crew cost, and how much are we paying these people, things like that. I think I just tangentially got into that, but I do have other videos on my channel that speak specifically to that. If you're scheduling people that work in a grocery store and some people make more per hour, you might want to minimize the time that they work and use a little more resources from the people that are cheaper. Otherwise, you're going to be paying the people that make more money a lot of money, and could impact your business. Okay, you don't want to take too much business away from other people, because if you give them no hours, they're probably going to leave and go work somewhere else. But you don't want to give them all the hours too if you're paying them more to be there, okay? So there's a bunch of constraints that we have to handle. And finally, we're going to need to solve everything using scipy.optimize. I'll show you how to do that. This is a linear programming, or scipy minimize. That's another library in the Python family, or Python network, whatever you want to call that, Python landscape, that handles minimization problems. And a negative minimization problem is a maximize problem. We're trying to minimize these problems, right? And if you're doing linear programming, more like scheduling people to work at the grocery store or to work for an airline, the linear programming tool will help us with that. So that's the setup here. Here's the execution. We have 4 pilots, 16 flight attendants. You can fly 3 to 4 flights per day. Each flight has a scheduled departure and arrival time. Each crew member has a rest or turnaround time constraint. Okay, we need to assign crews to flights in ways that covers all the flights, ensures no overlaps. A crew member can't be in 2 places at once, obviously, right? That's physically impossible. Respect constraints. This is the rest time and the maximum flights per day, and how much time you get to move from one airplane to another airplane as you're disembarking the plane that just arrived and getting ready to get on the plane that's getting ready for departure, and optimize the fairness, cost, and utilization of everything. Okay, so I don't have all these airplane details. This is, within the business, confidential details about that, right? And personal to the business. Obviously, I don't have this. So I'm going to create some synthetic data that represents a real world scenario. So I have departure times over here, arrival times, required pilots, and required attendants on each flight. So we're going to assume 4 pilots, and we have 2 per flight and 4 attendants. And we can choose between 4, which is actually 5, and 20. So you can see we start with 0 is actually 16. Yeah, 4 to 19 is actually 16 flight attendants and 4 pilots, so 20 total. So let's go ahead and create a matrix of feasibility to determine who can be on what flight, what are the previous flights, what's the minimum turnaround time. We're saying 60 minutes. If you need to change this, you can go ahead and change this constraint. If you want 2 hours, that's 120 minutes. If you want 60 minutes, that's 1 hour. So we have the flight departure time minus the arrival time divided by the total number of seconds divided by 60. This is going to give us the feasibility matrix, and we loop through each element here to see who's available, when, where, how, why, and everything else, right? So we have the feasibility matrix right here. I'm going to hit Control Enter to refresh this. So we have the A equality list and B equality list, and we're looping through all the elements in I and J. So I and J represent rows and columns in this in these data structures that we're working with. We have the rows of pilots and then the rows of attendants. This is short for airline attendant. And when I hit Control Enter, we can see feasibly every airline attendant and every pilot and where they can be scheduled and when they're available. And then obviously if it's a 0, it's not available for that individual given the constraints that we defined above. So it looks like I'm gonna have to refresh something. It's not displaying. I'll do that in a second. We use binary integer programming in the pulp library to help us solve this problem. We have the constraints I defined before. So 3 to 4 flights per day per crew, mandatory rest, matching airport locations, and fair distribution of work. So let me go ahead and save this and then do a refresh so we can see everything below. Okay. So, okay, skip down to where we left off there. Okay, we just did, oh, we didn't solve this problem yet. Okay, so that's where we left off. So here we go. We have the flight ID, departure time, arrival time, origin airport, destination airport, required pilots, and required attendants. Now, in the real world, this is going to be slightly more complex. You're going to have more flights, more departure times, more arrival times, right? You can have a huge network of airplanes going all over the United States, right? All different intervals, and this problem is easily solvable for the all the flights for Alaska Air and JetBlue and Southwest and all these guys. We're just trying to keep it simple and straightforward just in this example so you can understand it. If I was going to work for an actual airline, then they dumped a bunch of data on me, then obviously like the problem would scale up. But fundamentally, it's still the same. You would have more origin airports, more destination, more pilots, more attendees, more departure times, more arrival times, and more flight IDs. But essentially, this is a concept, right? You'd have 1, 2, 3, 4, 5, 6, 7. You'd probably have 7 features in your data set that you work with that's going to help you solve thousands, maybe even tens of thousands of different problems, right? Then you have the crew ID, role, and then the base. And I believe we are going to merge these together. No, we don't even have to do that. In this case, we are going to set the linear programming problem as crew scheduling. We're going to minimize the problem here. So we minimize the time between flights, minimize the number of people on flights, minimize the number of flights, right? That's kind of predetermined anyways. When you schedule a flight, usually you do it at least a month or a couple months in advance. Otherwise, you pay through the nose for these tickets, right? If you get it at the last minute. But all these flights are scheduled months in advance, right? So that's all set up for you. So we're trying to, that is a problem. We're trying to minimize all these problems or this specific problem based on all the constraints that I described above. Again, looping through the columns and the rows in this data frame. That's what the I and J represent. For J in length flights. So this is flights is over here, right? So this is data frame. So we're looping through all these elements. The I is crew, for I in length crew. And if you look at the length, really it's just this right here. If I display it, REW, and let me display flights as well, just so you can see what this thing looks like, right? And let me print something in between just as a separator so you can see the first and then the second data frames here. Okay, I think it just makes the breaks it up a little bit nicer. Okay, so here's the flights, right? We're looking through all these columns and all these rows down here, and here's the crew down here, pilots, and then the base airport, and then the destination airport, and then we actually have a third. What was the third? Let me see this thing here. So display. Oh, the display assignments. So those are the crew assigned to the plane. So we have the flights, we have the crew. Let me put another breakdown here just so you can see the distinction between these. So you have the flights. Okay, here's the crew, and then here's all the assignments broken up by this little hyphen dot thing. Looks like a bunch of ants on the screen, right? So we're looping through all the columns and all the rows to make all of these assignments. So we go through all the columns, all the rows of crew, columns and rows of flights. Go ahead and make the assignment right here. The assignment comes from the data frame and all the I's in the length of crew and all the J's in the length of flights. Okay, so this is how we go ahead and solve the problem. And the problem is solvable if it wasn't. For instance, if the time between flights was too little, less than 60 minutes, maybe 30 minutes, maybe 25 minutes, you're getting more productivity out of your employees, but you're probably going to burn them out, number one. And if one arriving flight is a little bit late and you only have 25 minutes to get across the entire airport to catch a connecting flight, there's a good chance you might miss it, right? So we don't want to make the problem so optimized that either number one, we can't solve it, or number two, we can solve it mathematically, but realistically, maybe a bunch of flight attendants or pilots are going to miss their next flight. We don't want to set them up for failure. So we're going to keep that 60-minute constraint. But my point is the problem is solvable given all these constraints. Otherwise, you would have an error. You would know that real quick if you had an error. Okay, so this is comprehensive crew assignment schedule where each crew ID is assigned to a specific flight ID. The assignments obey maximum flights per day, required crew per flight, no overlapping flights. That would be impossible, physically impossible, right? And the turnaround time constraint is set at 60 minutes. So let's go ahead and create a plot here. I always say the same thing. Picture is worth 1,000 words. When we look at this picture, we see the flight ID. We see the ID based on the color of the label over here. This is called a Gantt chart. If you don't know what a Gantt chart is, I would invite you to take a look. These things are pretty cool, and they help you understand from a project management perspective or from a timing perspective how everything flows. Okay, so if you look at this green one over here, you can see some overlap. No, let me look at this. This is a simpler version over here. Okay, so here you see the Gantt chart. You have market research, specifications, planning, design, development, training, assessment, and documentation. And you can see there's a little bit of overlap. Anytime you have green overlapping another green, there's some overlap there, right? So sometimes these projects can move along in parallel. Sometimes you have to wait for a definitive end date before you can begin the next part, right? So here you have market research and specifications overlapping a little bit. Specifications and planning design overlap a little bit, but market research and planning and design overlap not at all, right? So zero overlap. So market research has to be done before planning and design can begin. That's what this says. So this Gantt chart here is similar. We have the flight ID is flight 0. You have crew member pilot 1 and pilot 2, then attendant number 4, attendant 12, attendant 13, and attendant 19. Now, we probably have people's names associated with this, although maybe it could be people's IDs, all right? So the person's ID they would know what their ID is and you could identify them that way. But we'd probably have people's names associated with this, right? So here's the next flight. We have pilot 0 and pilot 1, and then 4 flight attendants over here, pilot 1 and pilot 3, okay, and then the flight IDs over here. Then we have pilot 0 and pilot 2 over here, and then we have the 4 attendants down here, right? And the gap in between is at least 60 minutes, so they can get from one flight to their other flight, the connecting flight. So these 20 people, 4 pilots and 16 flight attendants, are all different individuals working for the same airline. A crew usually refers to a group of assigned people, right? Persons to a specific flight, where you'll typically have 2 pilots and 4 flight attendants on one specific flight. You always have 2 pilots. I heard this a long time ago. I didn't know it until until I heard it, but it makes sense. You always have 2 pilots in case one of them passes away mid-flight, God forbid, but people can pass away anytime. There's no promise for tomorrow for any one of us, right? So if the pilot dies mid-flight, you want somebody to land that plane. Otherwise, everybody in the fuselage is going to die too, right? So you need 2 pilots. So you always have 2, and then the flight attendants can be any number. I've seen just a couple on smaller flights. 3 or 4 is pretty common, up to several, right? If you're taking a big international flight and going several hours. So that's that. So we can also simulate crew teams across multiple flights. So we saw all the same crew on the same flight here, but remember, a crew can basically be a group of people assigned to the same flight. So we can have team A, team B, and then we have the I's and J's over here. We're grouping through or looping through all the elements of the crew data frame and the flight's data frame, just like before. And we're creating all of these flight assignments. That's what that's called. So when I hit this, Control Enter, you can see the results down here is the flight assignment. So you have the role, the flight ID, start, end, crew, label, and then the team. And again, remember the I is for the index of the crew member. So crew.location I gives you the ith crew member, right? So you iterate through every single element of this data frame. And the J does almost the same thing, but it also gets instead of the crews, it gets the flight data frame. This is how we assign all the crews and all the flights together to get the, what was this called? The, assignments. So you get the assignments data frame, right? So that's how we loop through all the I's and all the J's. We get the assignments down here. Let me hit Control Enter to refresh this cell. And then we have the team members, team A, team B, and then other or unassigned. And if I create a Gantt chart based on this, you can see the color represents the team. So this is team A. They're flying in the morning, early afternoon, or late morning, and again in the afternoon. And then in the evening, that's team A. Team B is represented in red, right? With the at least 60-minute gap in between, right? And we've handled all those constraints. And then the other or the unassigned is in green. I guess other is green. There are no other assigned plotted up here. But you can see over here, you can see all the people on the flight, right? So the blue, purple, orange, and yellow are people on the flight, or airline team members on the flight. And here you see the different teams on different flights across the day, okay? So we can go ahead and refresh this, and we'll look at one more visual. This shows us Z, X, and Y labels. So the X is the crew member. These are all the columns. The Y is the labels of the crew member. These are all the rows. And the matrix values are the Z numbers, or Z letters represented as numbers. And this shows the number of times that crews flew together. So it could be 0, 1, or up to 2 times in this case that crews can fly together. Again, I'm going to create a just a small little matrix over here using the I's and the J's to get all the X labels, all the Y labels, and the Z's are going to represent the counts that per day that crew members fly together. So we'll see this, it's working. I should spell a result right now, actually, and we can see down here, and 2, we have 2 crew members flying, crew 9 and crew 3. Here we have 13 and 2, 17 and 7, 7 and 17 again, and here we have 2 and 13, and then 3 and 11. Oh, 3 and 11 there, and 2 and 13, right? So that's why they show up 2 times. All the others are 1 or 0 flying together. You have different crews assigned to different flights, right? So that's it, guys. In a nutshell, that's how you can optimize the schedules for airline pilots and flight attendants. Again, minimizing the time between um, disembarking from one plane and embarking on the next flight, minimizing the time spent in the airport, the downtime, but giving enough time and flexibility to the crew to rest and relax a little bit. They have to relax after a long flight too, just like the rest of us. And how to have all the flights scheduled and arranged and optimized so the business runs smoothly and you save money on fuel, on scheduling, on downtime, on salaries, right? Maximizing utilization as well. So we hit all these targets. So good job, guys. Mission accomplished. Um, we did it. Okay, so that's it. I'm going to wrap it up here. Hopefully the audio works today. Last time I recorded the whole video, threw it up on YouTube, and then there was no audio. Hopefully the audio works. I'll go ahead and check that. And that's it, guys. So I'm going to wrap it up here. I will post a video later today. I'll post all this code so you have access to all this. You can copy and paste it in your own environment. I'm going to stop the video here. Thank you so much for your time. I really appreciate that. And I'll see you in the next one. Bye for now.